Hi, today we are looking at the second condition of equilibrium, which deals with torque. So we'll learn about torque first and then use it to apply to our second condition of equilibrium. So torque is a vector quantity. It's measured in newtons per meters. However, our direction is different from most vector quantities we've dealt with to date, because instead of a direction like north, south, east, west, we are actually looking at a rotational direction. So it's a force that is trying to or will cause a rotation of an object. So our directionality, it tends to be clockwise or counterclockwise. Now our formula for torque is torque is equal to the distance from our fulcrum times our force, where r is the distance in meters from a point of rotation, or our fulcrum, and F is our force perpendicular to our lever. So if I have this lever, we can see our fulcrum is this triangle. Our R would be how far it is away from the force is from that fulcrum, and our force would be how much our force perpendicular to our beam or lever. Now, like I already mentioned, we don't use the same directionality for torque that we have used this far in physics. Instead, we refer to torque as acting clockwise, which is a negative torque, or counterclockwise, which is a positive torque. Now we can see we have a diagram here. So if I'm going clockwise, I would have a positive distance from the fulcrum, but a negative force. Multiplying those together, that gives us a negative torque. So clockwise, we'd have a negative torque. Where if we look at something going counterclockwise, we would have a negative distance from our fulcrum, but also a negative force in this case. So we'd have a negative times a negative, giving us a positive torque. So we'll look at some examples. So if a child on the left has a mass of 35 kilograms, what torque are they exerting on the beam? So we just have torque is equal to radius, or our distance times our force. Now in this case, our force is the force of gravity acting on the child. So we've got our torque is equal to R times M times G. Substitute in our values. Our R is negative because it's to the left of our fulcrum, or point of rotation. And we get torque of 206.1 Newton meters. However, we were just given values to 2 sig figs. So 210 Newton meters. Okay, next we've got center of gravity. Since most objects are not so narrow that they only occupy space at one particular measurement, we use the location of their center of gravity as the point at which all force is concentrated. For most objects, we'll consider the center of them to be the center of gravity. Now, our second condition of equilibrium is known as rotational equilibrium. So this occurs when our sum of our torques is 0. So in this situation, the object is either not rotating or rotating at a constant rate. So we have the same diagram as before, but in this case, if the child on the left has a mass of 35 kilograms, the child on the right has a mass of 20 kilograms, and the beam has a mass of 15 kilograms, what distance from the fulcrum must the child on the right be to have rotational equilibrium? So we know that sum of torques must be equal to 0, and we have torques in this case coming from 3 places. So we're going to have torque A plus torque B plus torque C equals 0, where torque A is one child, torque B in this case is a beam, and torque C is the other child. Now we can fill in our torque equation for each of those. So RA FA plus RB FB plus RC FC. Now we want to get RC on its own. So I would move RAFA and RBFB to ever solve our equation by subtracting them. At this point, divide both sides of our equation by FC, and in this situation, all of our forces are being caused by gravity, so we can replace all of our forces with mg. And then we fill in our values, and we get 0.68 meters. Okay, next example. If a beam is 4 meters long and has a mass of 15 kilograms, what is the tension force in the cable? And we can also see it's holding up a 25 kilogram mass. So, once again, we know sum of torques is 0, and we're going to, once again, have 3 torques. You're going to have a torque from a beam, a torque from the mass, and a torque from the cable. Now we want to solve for a component of force that is in torque C, so I'd rearrange to get torque C on its own, and then substitute our equations in, and then divide both sides by RC to get the force at C. Now our force at A and force at B are both gravitational forces, so they can be replaced with mg. So at this point we can substitute our values in, and we get the force of C is 257.5125 newtons. However, we're not finished, because that's just our perpendicular component, but our cable is attached at an angle. So I would draw out a triangle to represent our cable, so we can see that upwards we've got a force of 257.5 newtons. And essentially an angle of 55. We want to get the hypotenuse here, and we have our adjacent, so I would use cos. So we want to solve for hypotenuse, so I'd get out of our denominator by multiplying both sides by a hypotenuse, and then divide both sides by cos. Substitute our values in, and we get a force of 450 newtons.